All right, this pencast will pick up from where we left off in class with the solutions to homework 2 on algebraic fractions. So continuing with number 4, we're looking for the least common multiple of 18r squared s to the 5th, 24r to the 3rd st squared, and 15 s to the 3rd t. And I'm going to proceed with the process illustrated by the definition, which never changes for an LCM. It is the product of all the unique bases evident in all the terms prime factorizations, each base raised to the highest power evident in all the factorizations. So the first thing we're going to do is look at the prime factorizations of all the monomials. So we'll just write these here. And 15s cubed t. The only caveat on this is to write the factorization using exponents. So 18r squared s to the 5th, 18 is 2 times 9, so that's 2 times 3 squared. And the variables are already in exponent form, so all you're doing is copying them straight over. So the only work is to do the prime factorization of the coefficient. These come right over unchanged. So continuing with the other ones, 24 is 3 times 8. So that is 2 cubed times 3. Carry over the variables, r cubed times s times t squared. 15 is 3 times 5, nothing happening there. Carry over all the variables. Now, as said, the least common multiple. How many different bases do you see? Well, looking up and down all these lists, I see a 2, I see a 3, and I see a 5. So I have 2 times 3 times 5. I also see an r, an s, and a t. Times r times s times t. Now stop, take a breath, and find the highest exponent that you see. Looking at the 2's, look, what do you see? The highest exponent I see is 3. That one is right here. Now look at your 3's. I know it's getting a little harder with all the writing on the factorizations, but the highest exponent on any 3 is a 2. And that one was right there. And now look at your 5's, or 5 singular. So the highest exponent is 1. You're free to write that in or not. Quick multiplication, and you're looking at the LCM. 2 to the 3rd is 8. 3 squared is 9, so 8 times 9 is 72 times 5. 0 carry 1, 360. And let's look at our variables. So look at all your r's. What's the highest exponent that you see? I see a 3 as my highest exponent. That one is right here. Now look at all your s's. Highest exponent that you see. I see 5 as my highest exponent. That one was right there. So s to the 5th. And t, the highest exponent I see is 2 right there. So that gets a squared. Can't do anything with the variables. They're already in exponent form. They are part of your LCM, so just bring them right down. So the 360 was where the real work was, but r cubed, s to the 5th, t squared. The multiplication dots are, of course, optional, so most people would write 360, r cubed, s to the 5th, t squared. Box it, and a happy face. Same game on this one. We're looking for the least common multiple of this expression and this expression. And it's hard not to try to do something different because we're dealing with trinomials. We're not dealing with monomials or terms, numbers, exponents. Doesn't change. Take each of these and factor them. If you were to do a factor tree on these, it would be cumbersome, if not impossible. So a factor tree is really a mechanism for getting the factorization of any number or term. So really, are we hearing factor enough? Factor this mess. So take out an x, and I get x squared plus 5x plus 6. Continuing with the factoring, the x is part of your factored expression, and I get what? X plus 3, x plus 2. That's it. Looking at the other one, I get x squared plus 6x plus 9, and I get x plus 3, x plus 3. Now you will be misled when you determine your LCM if your factors are not written using exponents if possible. So that is the proper factorization of the x plus 3 base. Now your LCM equals, look at all the different bases that you see, and we're looking at this factorization right here and this one, the final factored form of both expressions. So as we look, I see an x, I see an x plus 3, I see an x plus 2, and I already said x plus 3. So all the unique bases that I see are x, x plus 2, x plus 3. Now it's time for exponents. Look at your x. What exponent do we see? 1. The 1 is, of course, optional. It's good to put it there for explanatory purposes. X plus 2, what's the highest exponent that you see? 1. Again, the 1 is optional. And this is where writing the binomials using exponents, if possible, will protect you from being misled. Otherwise, you'd have 2x plus 3 bases. I guess you would just multiply them together. You'd still get the same answer, but a little more roundabout. So 2 is the highest exponent I see, so that's it. My LCM is x, x plus 2, x plus 3 squared. And I'm okay in that form. If you went ahead and FOILed it out, that's fine. But no, this should be good enough. Oops, happy face. Now we're done. This problem shows the use of the LCM because really the LCM is the LCD. So the LCD is the LCM of the D's. So when you're finding LCMs, you're really practicing to find the least common denominator. So forgive the quick handwriting, but let's get this done. There's a lot of steps in these problems. So 15y squared has a factorization of 3 times 5 times y squared. And this one is 2 times 3 squared times y. The LCM, all the bases, I see a 2, I see a 3, I see a 5, and I see a y. Now the exponents, I see a 1, I see a 2, I see a 1, and I see a 2. And then just multiply that out so it looks good. 2 times 9 is 18. 18 times 5 is 90. Y squared, that's my LCM of the denominators, making it, of course, my LCD. So as we did in class, rewrite plus, boom, 90y squared, 90y squared. And now start talking to yourself. Ask yourself, self, how did I get from here to here? And the answer is, I multiplied by 6. So I'm going to times 6. And then here, how did I get from here to here? Whoops. Multiplied by 5. So we need to make our numerators now equivalent with the 90y squared denominator. So 7x was already there, it was already here, and I'm going to multiply it by this 6. I'll clean it up in a minute when we finally add these two. So the x was already there, that was here, and I multiplied it by this 5 right here. Let's clean it up. 42x over 90y squared plus 5x over 90y squared. Please resist the temptation to start reducing and canceling. All you're going to do is go backwards. If you start to mess with this one, start reducing it, you're going to wind up with that. And if you do it here, you're going to wind up with that. We can't do that because if you reduce it, you lose the common denominator-ness. Since I have common denominators, I can simply add straight across 42x plus 5x over 90y squared equals 47x over 90y squared. I don't believe there's any simplification evident with 47 over 90, and the x and y squared obviously are unlike. So, box, happy face. I think we've seen these kinds of problems enough not to be intimidated by them. They are compound fractions. So here, let me just sort of darken the main fraction bar. So this problem will entail adding these together, getting whatever we get, adding these together, getting whatever we get, and then dividing this answer divided by this answer. right there. So let's start and kind of deal with it separately, and I'll stay with the separate colors. So the numerator, we'll do it down here, 1 over x minus 1 over, 1 over y. Common denominator should be evident as xy. xy, what did I do to this x to get the y? I multiplied by y, multiply the numerator by the y, and I get that. What did I do to get from here to here? I multiplied by x, multiply the numerator by x, and I get x, and this sum is y minus x over xy. Similarly, let's tackle the denominator over here to the right. 1 over 1 plus 1 over x. You can't get a common denominator unless everything has a denominator. Pretty clear that your common denominator is x. The right-hand fraction was unchanged. The bottom one, I multiplied the denominator by x, so I multiply the numerator by x, and I get x plus 1 all over x. Now, as we said in the beginning, let's take the numerator sum, because it's one fraction, y minus x over xy. Let's put it over the denominator sum, x plus 1 over x, and do what we know to do. That's going to equal, and we come over here, and we get y minus x over xy times x over x plus 1. Let's go straight across, and I get x quantity y minus x over xy quantity x plus 1. And as I stand back and look at that, I get a little more simplification here and here. So go ahead and do that, and I'm allowed to do that since both x's that are being simplified out are factors of their respective expressions. So this becomes y minus x over y x plus 1. Please resist the temptation to simplify these. This y is a factor. This y is a minuend. You cannot cancel minuends or addends. You can only cancel factor with factor. So no box around this one, too much writing, but still a happy face. Now this one will show the importance of finding the least common denominator when each of your denominators is a polynomial. So we have here a trinomial and a binomial. This one, of course, is already factored, but let's follow the process nonetheless. So x squared plus 4x plus 4. Factored form is x plus 2, x plus 2. Factored form using exponents is x plus 2 quantity squared. X plus 2 is simply x plus 2. If you'd like, you can put in parentheses with a 1 just to make it look like it would fit the rule. The LCM is the product of all the unique bases, which in both cases, the only base we have is x plus 2, so that's the only base in our LCM. Pause, remember to do the exponents. The highest exponent that we see on any of the bases is that 2. Therefore, that's my LCM. Re-express the fractions using that least common multiple as your common denominator. We have that. Now we go from this denominator down here and say, what did we multiply by to get from this denominator down to that one? And it's times 1. Times 1. Here I have my 5. What did I multiply by to get from this denominator, to that one? And that would be x plus 2. Now let's put them all over the common denominator. 6 plus 5, x plus 2 over x plus 2 quantity squared, and then just continue the simplification from there. So I get 6 plus 5x plus 10 over x plus 2 quantity squared equals 5x plus 16 over x plus 2 quantity squared. A quick double check that no further simplification is necessary, which it is not. Therefore, happy face time. This one much more similar, to the last one. The only difference being we have a variable in this numerator. Otherwise, it plays out very, very similarly. So x squared minus x minus 20 factors to x minus 5, x plus 4. X plus 4 is already factored. X plus 4, parentheses would look good. LCM is x minus 5, x plus 4. No exponents on any of the bases in the factored form. That is our LCM. Rewrite, and we get x minus 5, x plus 4, x minus 5, x plus 4. We have this numerator from here to here times 1. We have this numerator from here to here. We multiplied by x minus 5. Put it over the common denominator, simplify it out, see what happens. So I have x plus 2 quantity x minus 5 over my common denominator, x minus 5. X plus 4 equals x plus 2x minus 10 over that denominator. Equals, what am I going to get? 3x minus 10 over x minus 5, x plus 4. That's it. No further simplification possible. Happy face. This one again, the highlight for this one would be to watch what happens with this minus, and then you'll see why I write my numerators the way I do when I combine. It's when you subtract, writing the numerators the way I do will prevent you from making a negative error. Watch, and I will point it out. So x squared plus 5x plus 6 factors to x plus 2, x plus 3. X squared plus 4x plus 4 we already saw on an earlier problem. I know it factors to that. You do too. Least common multiple, bases, exponents, boom. Rewrite, boom, boom, boom. X plus 2 squared, x plus 3. X plus 2 squared, x plus 3. My existing x, what I multiplied by, that would be another x plus 2. There's my 2. What did I multiply by? An x plus 3. Now, when I combine over the common denominator, you'll see why I do it the way I do it. And I would strongly suggest you do it that way also. Plus 3 over common denominator squared x plus 3, because at this stage we all know you're going to distribute that. The common student error that I'm trying to help you avoid is just applying the negative to the 2 and not to this distribution. That would be a mistake, and that's what happens if you don't do the numerators the way I do them. I'm not saying that it will happen, but experience has shown that it happens a lot. So simplifying the numerator, we get x squared plus 2x minus 2x minus 6 over that denominator equals, now I'm going to swing back over here. I think we see that those go bye-bye. X squared minus 6 could factor to x plus or minus root 6, but that's not going to help us. We will just do this. And a slightly messy answer, but still a happy face. Nothing really interesting or nothing to be careful about on this one. There's 3 add-ins. Factor is just slightly more complicated than the other ones. So let's look at our denominators. In fact, it's so routine, it's kind of boring. Oops, I put my parentheses on that one a little early. So let's do that. X squared minus 3x plus 2 equals x minus 1, x minus 2. Now that's convenient. So my least common multiple is this. Double check that I didn't make a mistake. No exponents. Life is good. So rewrite. Don't forget the sound effects. It always helps. It's tedious writing the denominator. Tedious. All right, new numerators now. So that's x plus 1 is my existing numerator. And in order to get that common denominator, I multiplied by x minus 2. X plus 2 is my existing numerator. I multiplied by x minus 1 to get that denominator. X is my existing numerator, and I multiplied by 1 to get that. Essentially no change. Now it's a FOIL fest and an alphabet soup in hell, so let's go for it. X squared plus, oops, be nice if I could FOIL correctly, minus X minus 2 plus X squared plus X minus 2 plus X. And you may be asking yourself, why didn't you put it over the numerator before FOILing it out? This would not have changed. I don't have that negative error to worry about. So I went ahead and did the FOILing and then combined them in the numerator in one step. Yes, you can do it in 2 steps. Do you want to have 2 processes, one for plus, one for minus? Maybe, because when you have 3 things added together, that extra step of combining over the numerator before distributing or FOILing is just extra writing. There's no impact of the operator on your FOILing or distributing. There is when you subtract. So maybe it's good to have 2 different processes so you can use the one that saves time when it's warranted. All right, back to work. Looking for simplification. What do I got? 2x squared. That's these. I hate doing this, but I'm going to anyway. Goodbye, goodbye, leaving me 1x. And then just minus 4 over x minus 1, x minus 2. Now, as I'm sure you're aware, you have to see if the numerator is factorable because further simplification might be necessary, and stopping short is an error. It's not fully simplified. Let's just do mental AC. So product AC is -8. Are there any factors of -8 whose sum is +1? The answer is none. Therefore, I can circle it and go happy face. The mental AC method is one way for checking for factoring. The other one is guess and check. Ugh, I can't believe my mouth made that phrase. And the other one is to see if the discriminant is a perfect square number. Take your pick. You have to see whether or not the numerator, when you're done combining at this stage, if further factoring is necessary. Your choice, though, on the method. This one, we're simply going to look at all the components we've looked at regarding common denominators and adding and combine that with compound fraction land. So it just increases the complexity, but the ingredients, if you will, really don't change. So red for the numerator, purple for the denominator. Let's get going. The denominator is already combined, so we don't have to do anything with the denominator. What I'm looking to do, by the way, is get in this original complex fraction form, get it into 1 fraction over 1 fraction, because then we can go a over b divided by, because a fraction is essentially a division problem, c over d, which we transform to d over c, and then proceed from there. So this little formula is worth having as a brain tattoo. All right, back to work. Red for the numerator. So it should be clear that my common denominator is x plus 2 quantity times x minus 5. So I have 1 over x plus 2 plus 1 over x minus 5. My common denominator will be x plus 2, x minus 5. And my numerators will look like x minus 5 and x plus 2. And the combination, since I have the plus here, I'm going to do the combination while putting it over a common denominator, which will give me 2x minus 3 over that common denominator. And we can do that. And I can switch right to copying down this right here. However, in case there is simplification necessary when I get to this stage, I would like to have the denominator in factored form. So we'll do that in the next step. Yes, you are free to do it at this step. Okay, so this original complex fraction has now been transformed to this one. And now we're going to get to this stage in green. I'm going to take the numerator, 2x minus 3 over x plus 2, x minus 5, and multiply it by the reciprocal of the denominator, which will be x minus 5, x plus 2, and yes, I factored this part of the denominator while I reciprocated it. Similarly, I'm going to factor this while I'm copying it down. The fewer steps that I write, the fewer chances I have to make a mistake. However, the more steps you do in your head, the more chance you have of making a mistake. So pick your poison. This one factors to 2x minus 3, x plus 1. And now before continuing, we kind of do what we all love to do and like, yay, yay, what else do I got? There these go. Look at this, man, I'm canceling left and right. Now remember, I canceled that in its entirety. That's why I'm putting parentheses around it, so you didn't think I was canceling addends, minuends, or subtrahends. This entire thing equals, let's go down here. There are no survivors in the numerator, so it is 1 over x plus 1. Happy face. And now a completely different, just a practice if you ever see this form and it ever helps, we are doing senior best couple. That is summarized with the phrase breakup, which I know is sad, but I still think it's funny. And what we're doing is we're taking each term here and putting it over its own common denominator, because it should be obvious that this term with a trinomial in the numerator and a monomial in the denominator could be expressed as three separate fractions with the same denominator. It's as though the given problem is the answer, and you're going back to what were the three fractions, what was the common denominator. So as I take a look at all of these, I get 3x squared over 60x plus 5x over 60x plus, sorry, that's a minus, as I'm looking carefully at my operators, 12 over 60x. And then just take all of those and simplify them. This one should give me, so boom, boom, that's going to give me 20. One of those goes, one of those goes. Please forgive the messiness. X over 20 plus, goodbye, 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 12. That's going to be what, 1/12 minus, boom, boom, 5, 1 over 5x. Caveat on this one, please, 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 please resist the temptation to write this as 1/5 x, because that's wrong, wrong, wrong. Grr. 1/5 x is equivalent to 1/5 times x over 1, which is x over 5. This is not x over 5. So be very careful when you're writing fractions that don't have any variables in the numerator and like a variable in the denominator. Make sure you do not write it in this form. This is called coefficient form. This is called rational form, and they are not equivalent. So quick rewrite so we can look at our answer a little more neatly. 1 over 5x, done. It should be clear for this one that we have this entire expression divided by, so we're going to be multiplying by the reciprocal of this one. However, we still need that a over b divided by c over d form before we can continue. So that is one fraction divided by another fraction. We know to transform that to multiplication. We got that. But we have to deal with this expression here and turn it into one fraction, and we have to do the same thing on the other one. So looking at that, I can do the rewrite in my head. Tell me you see that the LCM of the denominators, I should be writing LCD, but get over it, is 2x plus, whoops, I was too happy, 2x plus 1. And the LCM over here is 1 minus 2x. So for the left fraction, I have 2x over 2x plus 1, no modifications necessary because it already has the denominator that is the common denominator, minus 1 over 1, so that's going to be 2x plus 1 over 2x plus 1. So combining that, I get 2x minus 2x plus 1. You see what I'm doing now with the denominators? Sorry, with the numerator. I'm doing this extra step here, carrying the operator down and bringing this quantity down so that I don't mess up the subtraction. Where was I? Common denominator plus 1. So that should give me, if I'm looking at this right, negative 1, because that's going to distribute in, that's right, over 2x plus 1, divided by, now let's go over and do this one. So common denominator is 1 minus 2x, so I have 1 minus 2x over 1 minus 2x. See, converting 1 into a fraction is easy. It's whatever the common denominator is over itself. So plus, what, 2x over 1 minus 2x. I have this plus, so I don't have to do this step. So I should get, right, just 1, because this minus 2x plus 2x is gone, over 1 minus 2x. So this is going to be negative 1, 2x plus 1, divided by 1 over 1 minus 2x. Following our division of fraction rule, that's negative 1 over 2x plus 1 times 1 minus 2x over 1, and that is going to give me 1 minus 2x over, oh, sorry, I forgot my negative 1. Sorry. Got that over 2x plus 1. That's kind of a complicated answer. Switching the order of subtraction, what we called commuting subtraction, might help, but I can't see that right now. Here's my existing negative 1. Here's my commuted negative 1. And now I have 2x minus 1 over 2x plus 1. No, it didn't help. A little bit, right? 2x minus 1 over 2x plus 1. That's fine. Got it. Could you leave it in this form? Yeah, as long as you had this bracketed. Otherwise, it would read incorrectly. I would take this one. This one's okay too. It's not a bad idea to check and see if you could get further simplification by commuting the subtraction, but not at all necessary. By this time, you should see everything to do and everything to look out for. So let's remind ourselves that we have the subtraction of two fractions, so we're going to do that extra step with the numerators. Let's proceed with the common denominators. X squared plus 2x minus 8 is x plus 4. X minus 2, x squared minus 16 should be clearly obvious, as that, my LCM, is x plus 4, x minus 4, x minus 2. There are no exponents on any of the binomials, so that is my least common multiple. Rewrite x plus 4, x minus 4, x minus 2. Hardest part about all this is writing it all the time. X minus 4, x minus 2, existing numerator, whoops, that's a weird looking one. What did I multiply by? Looks like I multiplied by an x plus 4. Sorry, an x minus 4. That's what I get for not looking closely. Existing numerator, what did I multiply by? The x minus 2. Over the common denominator now, x minus 1, x minus 4 minus x plus 2, x minus 2, over that mess. And now it's just an algebraic nightmare. X squared minus 5x plus 4. This, I'm going to do a little foiling right now. That's going to give me x squared minus 4. And remember that entire quantity is being subtracted, so that's going to be minus x squared plus 4 over that common denominator. Okay, what do we get? Goodbye, goodbye. Looks like I'm going to get negative 5x plus 8 all over x plus 4, x minus 4, x minus 2. Nothing happening anywhere. You almost wish it would, like you get a more exciting answer, but no, it is what it is. Do not worry if you did not get this far or got this far and can't do this problem. It is just there as a challenge problem. You might remember this is that one question middle school problem from 1990 that my middle school students challenged me to write. So this is that problem. We're looking for what values of x makes this algebraic fraction 0, and additionally, what values of x make this algebraic fraction undefined. And the specifications are up here. So it's undefined when the denominator is 0, period, and it is equal to 0 when the numerator is 0, but the denominator is not. Okay, all of that requires, hold on to your seats, factoring. So for the numerator, let's start by pulling out this common binomial factor. See that x plus 3 exist in all three terms. It's as though there's a y in all three terms. Additionally, you could see a power of x to the first, common to all three terms. So let's go ahead and factor all that mess out and see what we get. While we're at it, notice that in the numbers, a 2 is a common factor to all three terms. So let us take out a 2x, x plus 3, leaving me, what's that going to be? 6x squared minus x minus 2x. Let me just double check that. I have an extra x in there, so let's take that out. Do this. Over. Now we'll go ahead and finish factoring the numerator in the next step. This, totally obvious, x plus 3, x minus 3. This one's still the difference of two perfect squares. That's going to be 4x plus 2, 4x minus 2. Let's just double check that. There's our 16x squared. Plus 8x minus 8x, gone, and minus 4. That's good, that's good, that's good. All right, next step is to factor the trinomial in the numerator. Nothing else changes. 2x, x plus 3. That's going to be 2x plus 1, quantity 3x minus 2. And then my denominator, double check that I can't do anything more. I cannot. So just copy it down. Do not cancel anything. Now stop and look at it. What are the x values that make the denominator equal to 0? So what you're really looking at is each of these binomial factors. What x value makes each one of those equal to 0? And those are your solutions to what would make the denominator 0. For the mathematically curious, you can look at the denominator, and see like, if I FOILed everything out, I'd get a fourth degree polynomial, 4 solutions. And here they are, x equals 3, -3, -1/2, and +1/2. Those are all the x values that make the denominator equal to 0. Similarly, in the numerator, we have x equals, what are the values that make the numerator 0? Same, you would get a fourth degree polynomial if you multiplied all that mess out. The 4 solutions to that polynomial would be 0, -3, -1/2, and 2/3. Now comes the interesting part. You have to go back here and go, what values make the denominator 0? Well, right here as said. So these values make the original fraction undefined. Easy, easy. If you are to jump and say these values make the given fraction 0, you skipped a step. Right here, but its denominator is not. So which of these values up here in the numerator list are also in the denominator list? Is 0? No. Is -3? Yes. Is -1/2? Yes. Those are the only two values that make the original fraction 0. It's the fact that if a value for x makes the numerator 0, you can't conclude that it makes the whole fraction 0, because it might also make the denominator 0. And please, 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 please resist the temptation to think that 0 over 0 is 1. It is not. It is mathematically indeterminate. It is undefined. All right, that's a wrap on this.